Hi everybody, welcome to our session on automated zero-day discovery in 2021, squashing the low-hanging fruit in widespread embedded software. Thanks for joining us. I'm Daniel dos Santos, and today I will be presenting with Shahar Menashe. Right, so who we are. As I mentioned previously, I'm Daniel dos Santos. I'm a research manager at Forescout. I have a background mostly in academic computer security. I've a PhD in computer science. I've done lots of academic publications in access control and intrusion detection and other things. But recently I moved to industry and where I've done some security research, vulnerability research, threat research. And I've been speaking at conferences such as Black Hat, ZIFCon and others. And I'm very happy to be talking for the first time at Hack in the Box and to present this work that we did in collaboration with JFrog, where we applied both manual and automated vulnerability discovery techniques to an embedded TCP/IP stack and found some interesting results, and we'll be discussing those with you during this presentation. But before that, I would like to hand over to Shahar to introduce himself.
Hi, my name is Shahar Menashe. I'm Senior Director of Security Research at JFrog, which recently acquired Vdoo, which was the previous company I worked at. Coming from a line of manual reverse engineering and exploitation, automated reverse engineering, hardware hacking, things like that. And basically the system we developed that's now running at JFrog, the automated vulnerability analysis system, found some of these vulnerabilities while running on some firmware images. And we wanted to share, the vulnerabilities and how exactly we found them automatically, and how you can achieve the same. Basically, what's the state of automated vulnerability analysis in the modern era in 2021.
So before we move on, I would just like to thank our co-authors, Stanislav Amin and Yos at the Forescout side, and Asaf and Dennis at the JFrog side, because they also had an important contribution to this research. Right, so what will we be talking about today? So first I'll present an introduction, a background on this research, what are the Infrahalt vulnerabilities that served as the motivation for this talk, and a little bit about how those vulnerabilities were actually found, to then pave the way for the automated vulnerability discovery, which is the main part of this presentation that will be presented by Shahar. And then at the end, we'll talk a little bit about mitigation for device vendors and network operators, and then conclude this presentation with some discussion and takeaways. Right. So let's start by discussing the embedded system supply chain, right? So when we talk about devices in Internet of Things or operational technology or any type of embedded system, there is a long journey between the concept of this device, their development, production, utilization, support, and retirement. And there are many companies and many actors involved in that, right? And that forms this supply chain for these different devices. And in several places of this supply chain, there might be issues that introduce vulnerabilities or weaknesses or any other types of problems within devices that are used in a network. If you talk at the development level, there could be naturally occurring vulnerabilities. If you talk at the production level, there could be injected backdoors. During utilization, there could be misconfiguration and so on. But we are mostly interested in the naturally occurring vulnerabilities part at the development, especially in vulnerabilities that affect widespread components, right, that are used by many actors in the supply chain of many different devices. And one of these interesting components is called a TCP/IP stack, right? And we have an image there on the right-hand side illustrating one of those TCP/IP stacks, which is basically a software component that allows the basic and foundational connectivity elements of devices. So basically, it implements the TCP and IP protocols and other protocols on top of those, right? And also below in some cases. And that usually gets coupled to RTOSs, real-time operating systems that are used in embedded devices, and other components of software components of these devices, right, to form actually the firmware of a device. But why would anybody target a protocol stack, right? So the interesting part is that they are widely deployed. So there are vulnerabilities that actually trickle down the supply chain to many vendors, as we presented before. these TCP/IP stacks are often used by many different vendors to produce many different devices, but the code of the stack itself comes from one single vendor. Currently, there's an absence of a software bill of materials, which is typically called an SBOM. So vendors and users are not really aware of all the software components that are on their devices, and fixes in the core stack either take a long time or might never make it to all the OEM firmware down the supply chain. Interestingly, these stacks tend to be very ancient, so 20, 30 years old. So there's a good chance of finding exploitable bugs, right? There are not many. Security was not the top concern at the time when this code was written. And also in most of this firmware and most of these devices, there is no actual exploit mitigation going on. So basically, they are protocol stacks are components that are externally exposed. They are often run as privileged and low-level components that have a high chance of having bugs. So if you combine dispatching issues, the long lifespans, the broad trickle-down issues, you basically have vulnerabilities with a very high lifespan, which means there's an interesting return on investment for an attacker to find and exploit these vulnerabilities. If you look at previous work on TCP/IP stacks, in the previous 3 years, more or less, so from 2019 to 2021, there has been a lot of work done on TCP/IP stacks, right? It started with Urgent 11, which was a set of 11 CVEs on the IPNet, typically run on VxWorks. In 2020, there was Ripple20, which was a set of 19 CVEs affecting the tracked TCP/IP stack, and both of them had critical vulnerabilities allowing for RCEs. And then, starting in 2020, we at Forescout started doing Project Memoria, which was a set of integrated studies into TCP/IP stack vulnerabilities that were focusing on different parts of these stacks and different stacks altogether, right? We started with AMNESIA 33, that was a set of 33 CVEs looking at open source stacks, which was something interesting at the time, and basically the supply chain effects of open source and not just closed source stacks. Then we came up with Numberjack in the beginning of 2021, which was a set of vulnerabilities related to predictable TCP initial sequence numbers in 9 different stacks, open and closed. Then recently we had NameRec, which was a set of DNS client vulnerabilities affecting 4 stacks. And what we're going to discuss in this presentation is called Infrahalt, which is a new set of 14 CVEs on one specific stack called Interniche. Right. So what is Infrahalt? So the target for this research was NicheStack, also known as Interniche, which is a TCP/IP stack, an embedded TCP/IP stack developed by Interniche in the 90s and acquired by a company called HCC Embedded in 2016. It's distributed in several flavors, such as IPv4, IPv6, a dual combination of both, and a light version. And it served as basis for other stacks, right, such as EMNet. So if you think again about the supply chain, it's even stack to stack in a way. So some TCP/IP stacks are derived from others and then end up in operating systems that then end up in different products. And even before starting this research, we knew that this stack was popular in OT devices because previous research by others had shown that it was used in several Siemens PLCs, for instance. The Siemens found a segment MAC variant that affected several devices, and that was called CV 2019-9300. And then there was some work by Ali Abbasi looking at the S7 PLCs and looking at actually the source code of Interniche that was found, that was leaked online, and they were able to actually compile this source code and have a look at it, but they didn't find any specific vulnerabilities in that, but it was the start of this work, let's say. Right. So what vulnerabilities did we find then in NicheStack? As I mentioned before, it's a set of 14 CVEs. So 2 of them are critical, allowing for RCs, and the rest is mostly related to denials of service, but there are also some related to DNS cache poisoning. We'll explain in the next slides how they are interesting. But there are 5 components affected, so DNS, HTTP, and TFTP at the application layer, and then ICMP and TCP at the lower layers. The interesting point is those vulnerabilities were found both manually and automatically, right? Some of them only manually, some only automatically, and some in both ways. So let's talk quickly about the RC. So the first RC affects the DNS component, and it was found manually based on an entry pattern from a previous research that we had, NameRack. So it's similar to one of the CVs that we had found before on another TCP/IP stack called NucleusNet. And the issue here is that basically the resource record length on DNS responses, called RD length, is not checked, right, for the size, basically. So an attacker can specify an arbitrary value for this RD length and then overflow the next field on the packet, which is the R data field. So if you look at the examples of code there is basically a man copy function that takes that RD length -1 and then writes that into the DNS entry PTR name buffer. But if you look at that buffer, it's actually of a fixed size, right? So you can see that in between those there is no check for the size of RD length. And this buffer is allocated on a heap, and usually there is no exploit mitigations, right? Which leads to the actual exploitation of this vulnerability, which was achieved with a classical unlink technique, because there's no safe unlinking. So basically, there's an example of a DNS packet at the right-hand side there, where you have name, type, class, TTL, RD length, and RD data. And basically, if an attacker uses the values that are shown in the figure there, test.com and type, class, TTL, and so on, and then provides an arbitrarily large RD length value, it can then provide shellcode in the packet that will be overflowing the R data buffer. And it's interesting because this is a DNS response packet, but it's easy to spoof DNS records that will be accepted by a device, because the techniques that are usually used to synchronize DNS requests and replies, which are the source port, UDP source port, and the transaction ID, are not actually random in this stack, right? Which are the other two vulnerabilities that we mentioned at the beginning. And which means that in the end, responses from any IP address are accepted and will be processed by the stack. And the shellcode that we developed actually uses the Stack API to perform TCP handshakes and send other malicious packets. And we'll discuss a little bit further on an attack scenario. But the actual exploitation using unlinking is shown quickly on the lower bottom of the lower side of the bottom side of the right hand figure there, where you corrupt the metadata of the top bin, and then basically there is a fake free chunk that is created also in this DNS entry structure, so that when there is a next allocation, that will go to this fake free chunk, and then that can be used to hijack the control flow and basically execute the desired shellcode. There are more details on the white paper that we have released together with this research on the Infrahalt website at Forescout, but that's basically a quick overview of it. So the next RC is related to HTTP, and this one was found automatically, and it occurs when actually the stack parses the HTTP post request URI field, which is highlighted in red over there. So a request string of more than 52 bytes causes a heap buffer overflow, and then the RC can be achieved similarly to the previous one, but it may require more careful heap shaping. But the details on how this one were found will be discussed later on by Shahar in the section on automated vulnerability finding. I just wanted to discuss a bit the attack scenario enabled by this type of vulnerability, right? Where if you have devices that are externally exposed and vulnerable to Infrahalt, and then you have internal devices that may also be vulnerable to other things and that are controlling critical operational technology processes, such as heating, ventilation, and air conditioning in a smart building, in a data center, or in any place that needs temperature control, for instance. When that device that is exposed issues a DNS request, an attacker can spoof then a DNS response with the shellcode that instructs this device to create a connection with the internal device and send a malicious packet, and then basically either again, use an RC on this one or just a DOS and then crash that so that the physical process is then disrupted, right? So this is the type of scenario that is enabled by widespread vulnerabilities in embedded systems that affect different types of devices and that are externally exposed. And we also have a video of the exploitation that you can have a look there on YouTube that has more details. Right. But let's talk about the supply chain impact that we started as a motivation, right? So if you look at the NicheStack offerings that we mentioned in the beginning, those are distributed and were distributed over these 20 years via many different companies and ended up in many ways in many products from many vendors. So those logos that you see at the end there, they actually come from the old and now archived Interniche website that mentioned their customers. And we're not saying that all of those figures that appear there are vulnerable, but some of them have already confirmed that they are vulnerable and others are still investigating and so on. But the issue is definitely widespread. So how did we actually find these vulnerabilities, right? So we had two types of input. We had the leaked source code of a previous version called 3.1 that we mentioned was used in previous research by Ali Abbasi and others. We had a binary demo of a more recent version that was previously available on the vendor's website. It was took down now, but it was publicly available at the time of this research. And we started with the manual analysis that was based on the known anti-patterns from the previous research, right? Amnesia 33, we looked at integer overflows, lack of bounds checks, and so on. Numberjack, we looked at the weak TCP ISN, and in NameRack, we looked at DNS compression and several other types of anti-patterns. And basically all of those were found in this new stack and found manually. We did not analyze IPv6, which is also an anti-pattern that we had previously seen. And this was a great result, but it was lots of work and potentially missed issues, right? Which is what motivated the automated vulnerability discovery part that will now be presented by Shahan.
Okay, so now let's talk about the automated vulnerability discovery part. Basically how our system was able to find some of these vulnerabilities, what are our methods that we suggest on, at least from our side, how to automate vulnerability discovery, and what technologies are available today for automated vulnerability discovery, and specifically how we will delve into how we found one of the vulnerabilities in an automated manner, how the system found it. So first of all, our method of operation of the system is going to be as follows. The system is going to map sources, that's user input sources. So basically these are variables and function calls that the system believes that are coming from user input or external input. The second step is going to be mapping dangerous sinks. That's what we call the leaf or the end of the flow, a sink function. So this will be a dangerous function or method or something that basically when it gets user input, you know there's an exploit going to happen. So for example, for command injection, it's going to be system or popen. For buffer overflow type vulnerability, it's going to be strcpy or memcpy, things like that. So basically, these are the dangerous functions. These are the sinks. And the third step is going to be to find an unfiltered data flow between one of the sources and one of the sinks. So we will touch upon what it actually means unfiltered, but basically it means that nobody is filtering out bad user inputs or malicious user inputs. And the term malicious really depends on what kind of vulnerability it is. Malicious in terms of buffer overflow isn't going to be the same in integer overflow or command injection. So we'll actually go on that. So for example, you can see in this diagram, here we show a source that is getenv, which for our intents and purposes, we consider that as user input because it's untrusted usually. So the source reads some data into a variable, and then there's a data flow from the getenv through some functions, basic blocks, etc., and it gets to the system sink. So in this case, it would be a command injection vulnerability. So this is the high-level operation of the system, and this is what we're going to discuss. And each part obviously has we can delve into each part individually. So let's start from the beginning chronologically. And the first step that we do is to convert the ASM, the raw assembly, into a high-level intermediate representation, fairly high level. It's not source code, but it's fairly high level. So for example, here on the upper right corner, you can see the original source. So we don't have the source because we have a binary, but let's say that the binary was compiled from this source. So it's called, it calls memset with some constants and referenced variable. It writes two null pointers, and then it calls another function, basically, with a different, with one of the variables that was nulled. So if we look at the assembly level, the disassembly, which is, what objdump gives us, or IDA or Ghidra in the basic listing view, we can see good old familiar assembly. In this case, it's ARM assembly. And of course, this is a bit harder to discern, even as a manual researcher. And that's why we have tools like the decompiler and things like that. But especially when you're using automated analysis, you have to convert it to a higher level anyways. You need to understand the function calls, the arguments, etc. So either you do it yourself by writing your own engine, or you use something like Ghidra's P-code analysis. Basically, when you decompile a function with Ghidra, it converts the assembly language into high-level P-codes. And there are all sorts of P-codes here. I'm showing this assembly converted to P-code operations. You can see it's 6 P-code operations, which is much better than this whole mess of assembly. And basically, the first field here is the output. The second is the P-code type. The third and so on are the inputs. So for example, in order to create a variable or reference a variable, there's the PTR sub P-code. And this causes the reference that we see here. It takes, this is the address of RCVDQ, for example, the second input. And this is a possible offset, but in this case, it's offset 0. And then it creates a temporary variable that has this name, or 10000004C. And you can see this variable is then in the second P code, which is a call P code. Here it's calling memset. So here Ghidra did the work for us and collected all the arguments for this call. So it calls memset, and then all the other inputs are the arguments. So you can see the first argument is this temporary variable that was created. So it's RCVDQ. And then the second and third arguments are constants. So it's very easy to discern. Here, for example, if we look at the assembly level, then first of all, because it's RISC architecture, then you can't put the whole 32-bit in one opcode. So it splits the address of RCVDQ to 2 opcodes. And the moves to the registers before the function call can of course be not very much adjacent to the branch. So these are all things that Ghidra takes care of for us. So here we can see copy operations. We're copying to global variables. So this is what these operations are doing. So we can see it's global variables because it's actually copying directly to memory, and constant 0. And in the last call, we also see another function call with another referenced variable. So This just makes analysis much easier, and basically our code takes the P code as input instead of the assembly. And this is also great for cross-architecture because basically it doesn't matter if the original assembly was Intel x86 or ARM or MIPS or PowerPC, we get the same P code. So we can just focus on the high-level intermediate representation. So the second part would be mapping the user input sources. This is a bit harder than mapping the sinks, which we'll get to. Basically, so we need to hypothesize on where user input is getting into the program. So for example, there's some high accuracy sources. So for example, if we see a syscall, like if we have the syscall names, or if we get them through divination that we'll see in a while. So if we have those names like receive, then we know that the second argument of receive is a output buffer that gets data from the network. So we can immediately say, okay, this is a user input source because we regard network data as user input. The same thing with getenv, and the same thing with fread, although these we regard as local input sources. It's reading from a file or the local environment. It might come from a remote source, but we can't guarantee that. So we regard them as local sources. Also, for example, and this is much more geared toward embedded devices, if you're reading from a well-known MMIO, memory mapped IO address, so for example, a specific address might be mapped to UART or Bluetooth, etc. And then you also know, okay, this is reading from that address is actually user input. There's a very cool Ghidra plugin called SVD Loader, which I highly recommend, which you can give the board name and it maps out, using public data, it maps out the address calls to the actual peripherals. So that's really useful. And other than the high accuracy sources, we also have score-based sources, which we try to accumulate a couple of these before we say, okay, this is probably user input. So for example, something that we use a lot is N2HS and N2HL, network to host short or network to host long. So these operations usually indicate that there's input coming from the network, and the program wants to convert them before it actually uses it, so integers. Of course, it doesn't mean it's network input 100%, but it's a good indicator that it might be network input. These are a lot of the times inline because it's like two opcodes. So we actually need to be able to identify them inline and not just as a function call. So I'll get to that. And there's also for example, if there's a function that references a lot of well-known protocol strings, which I'll show an example in a second, then we also regard that the arguments of that function as possible user input sources, and also the return value of that function, because we see that the function is messing around with a well-known network protocol. So an example for that, I took just two examples from like random binaries. So here we have an example of some HTTP strings being referenced from a function like content length, multi-part form data, and also FTP strings, user, pass, ACCT. So once we see these, again, we bump up the score for that function. And if it goes over a certain threshold, we say, okay, this is an interesting function. And then we can take all its arguments and return value as possible user input sources. And that also gives us more inputs. Another example that I didn't show here, but it's fairly obvious, is as an interesting function is the main call. So of course, anything that's coming to main, like argc and argv, or mostly argv actually, we can consider it as local sources because we know it's coming from external input. In this case, local user input, but again, external input. So For example, argv is another one of the local sources of external data. So regarding sinks, I'm just going to show a few. Of course, there's a ton, so it's not an exhaustive list at all. But basically, if we're talking about basic sinks, so command injection is super obvious. It's either the system call or popen call. So you know that if data flows into these calls and it's not filtered for shell meta characters, then of course it's a command injection vulnerability. So this is an obvious sink. Another one for buffer overflow is memcpy and strcpy. Again, strcpy. Here there's a caveat that, of course, the destination needs to be fixed size, and this is also something that we do, but I'm not elaborating on it because we don't have enough time. But basically, memcpy and strcpy, if we see a user input source flowing into it in the data flow analysis, then we say, okay, that's a possible buffer overflow. In memcpy, for example, we also check that the length is user controlled. Otherwise, of course, it can be truncated with a constant length, and then there's no vulnerability. A bit more advanced things is, for example, memcpy and strcpy can be inlined, or it can even be some copy loop, which is what I'm showing here. So this is a copy loop, and it has a custom exit condition. If the current character is equal to the at character, then it breaks. But this is also a copy loop, very easily distinguishable. And we need to take care of things like that as well. We can't just say, okay, it has to be a copy to strcpy or memcpy. So this is another example that we have to identify as a sink, and also integer overflow leading to a buffer overflow. So a sink might be two-stage, not just seeing that there's a system call, but rather seeing that there's some sort of possible integer overflow, maybe an addition without a check, and then that the data flows from that integer overflow to buffer operation like strcpy. So it's a two-stage sink, basically. So we'll show an example of that a bit later with the actual vulnerability that is automatically detected. So I said before that we use Unicorn in order to detect libc functions and other utility functions. And the way that it happens is that we use our own homegrown divination engine. And basically what this engine does is the problem is that if there's an RTOS binary or some binary which links statically to libc, you're not going to have any symbols like strcpy, malloc, memcpy, printf, etc., etc. And you need to identify that functionality in order to make your life easier, basically, when doing the static analysis. Like I showed before, for example, system is a sink, memcpy is a sink, getenv is a source. You want to understand these utility functions. You want to get these symbols, even if you don't have them naively. So what we do is we use emulation with test cases in order to determine which function we're looking at. So every unnamed function in the program, we define test cases. So for example, here you can see a test case for strcat. So basically we define inputs, and we define a test case. So allocating some memory with Unicorn, writing two strings to two different variables, and then calling the function, whatever the function is, because we don't know what it is really. It just has to match a given function prototype. So for example, in this case, it will test all functions that's getting two character pointers as input, so two arguments which are pointers, and then it will call the function with hello and world, and it will check that the test case will eventually check that the destination argument, which is of course the first argument, is the concatenated result of these both of these strings, and the second argument wasn't changed somehow. And of course, we have multiple test cases to verify that this wasn't a fluke. So for each for test strcat, there's also other test cases. But basically, if the function under test passes this test, then we say, okay, this is strcat. We just have to make sure that, to check that it's not strncat or strcpy, etc. So the test cases have to be very well defined. Okay, so now we're done with mapping the libc functions. We're done with getting sources and getting sinks. So the only step that's left is the final step, which is doing data flow analysis. So we're trying to figure out, we start with some source variable, and we're trying to figure out all the places that it propagates to. So if it's being copied, if it's being referenced in a struct, if it's being copied as a buffer, or not just by reference, by value, and if it's being copied to a global and then being read at. So basically everywhere this variable propagates to. And actually Ghidra provides a basic API for this. It's called get/slice or get/slice to pcode ops. It depends on what you want to get. But this is intra-function. So that means it will only work inside the same function. It will not show you where the variable propagates outside of the current function. It also doesn't work very well with stack variables. Sometimes it works, sometimes it doesn't, but it's a bit iffy. And basically, so here I've highlighted, phvar2, and you can see, okay, ivar3 gets the reference of that, and then n also gets some dereference of that, and then ivar3 is also mentioned here in n, so it will keep on checking, and phvar2 gets a dereference of that, of ivar3. So that works kind of okay, but only intra-function, only inside the current function. And of course, that's not good enough for us. So we expanded Ghidra's analysis to work inter-function. So basically, there's two major cases that we need to take care of. So propagation into child functions, propagation of the data into child functions, and propagation of the data outside of the current function. And again, we propagate this data to the whole program and check eventually if we reach some sync function, if any of the sources reach some sync function. So for example, let's look at an example here. So we have a source function, and it writes to the D variable. So now D is something that we track because it's a source variable. And then it calls F2. And what F2 does is copies the first argument into the second argument. So basically, D is getting copied into A. So if we look at it in the diagram, we can see that it calls F2 and then copies the source into another variable. But the question is now, okay, what's A? And A is actually an argument of CS1. So now we have to propagate upwards outside of the current function, CS1, and check, okay, where did we get A from? So this is obviously, recursive operation, so on and so forth. And this is an example of both going into a child and propagating out of the current function. And eventually we propagate into all variables in this manner and understand where, which variables are tainted by the initial variable. Okay, so let's say we have the data flow analysis down, but now we have to take care of a few issues. Like I said before, a lot of the times you can't be naive and just say, okay, there's data flow, boom, there's a vulnerability. Because in the real world, you add the size checks and things like that to make sure that there's actually not a vulnerability. So for example, in buffer overflow, it's obvious to add some size check if you're using strcpy, which of course you shouldn't, but embedded. So it does get used. So here there's an example of allocating a buffer with 50 characters. And then we still use strcpy, which is bad, but here we add an strlen check and see that if user input is over 50 characters, then we return an error and don't do strcpy. So this is a good check. Like there's no vulnerability here. But if I would look, at naive data flow analysis, I would say, oh yeah, okay. User input is getting to strcpy and buff is fixed size, then there's a vulnerability. So that doesn't work. We actually need to travel along the data flow path and look for these checks. And again, for each type of CWE or for each type of vulnerability, we'll have a different check. A check for against command injection, for example, can be seen here. So for example, here, user input is getting checked that if any of these characters appear in the user input, so asterisk, semicolon, backtick, $, blah, 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 then it's a shell meta character and we return an error. So this is also a pretty good check for command injection. I'm not saying it's checking everything, but it's a pretty good check for the basic stuff, and we need to take that into account as well. And there's also what we like to call data anchoring. So for example, sometimes you have a user input, but actually it's getting checked to be matching to a very specific thing. And after that point, it's not really considered user input. So for example, in the third example here, we can see if the user input is not equal to fixed input, like the string, then it returns an error. So from this place forward, I actually know that user input, it has to be exactly the string fixed input. So from this place forward, I don't tag this variable as actual user input or external input, because it has to be a very specific constant input. So from this place forward in the program, from the analysis side, it's regarded as a constant. It's not really interesting anymore. Okay, so let's talk about actually detecting one of the vulnerabilities from Infrahalt. So CVE 2021-31-228 is an HTTP server denial of service. And it's a signed comparison leading to overflow, a well-known CWE that we all love. So it's here's an excerpt from the code. It's pretty obvious. So we have the function getBound search. Here len is actually user controllable, and I'll show why it's user controllable. And here we have an if condition. If len is smaller than some boundary length, then do the mem copy. So this looks kind of fine until we realize that len is an integer and boundary len is actually also an integer. So this is a signed comparison and not unsigned. So if len is negative, this branch will be taken, which is bad. It's not supposed to happen. And then we have a mem copy with a negative value here, which is a huge unsigned value, of course. And then we get a denial of service because we get a huge memory copy operation. So the source here was detected via the score-based method that I showed earlier. So this is actually the same function that I showed earlier. Here, the score was high because of two factors. There's HTTP strings here. And also, there's a function that was, after the dynamic divination, was mapped out to be A to L. So it's, again, one of the functions that we upgrade the score because of, like I said before, like N2HS, et cetera, because usually when converting a string to an integer. That string usually comes from user input. That's why it's, of course, score-based. So we accumulate all these things. But here, A2L was detected using the dynamic analysis engine. So that's great, because in some binaries we had symbols and other binaries didn't have symbols, but the system still detected it. So after A2L was detected, this was detected as a source variable, and now LVAR7 is a source variable. You can see it's being written to a struct here. And then basically we follow that struct. We follow that struct with data flow analysis. And until we get to that sync function, which I'll show again in a second. So this is the data flow analysis part, just tracking the various copies and references and dereferences of this variable throughout the program. Even the first reference was even a data reference, which we also track. It also affects the score, but it's tracked. So here, it's interesting to see why we chose dynamic divination, for example, to detect A2L and not static. So I'll open up this code, just 1 second. Okay, so now that we have everything together, basically, like I showed before, the data flow analysis reached the get bounded search function, and the second argument is tainted by that initial source argument that's coming from A2L. And this vulnerability was classified as a signed comparison. Why? Because as part of the data flow, we went through this line, this if. And of course, we know whether it's a signed or unsigned comparison. There's actually a different P code for each one, for signed and unsigned, so that's easy. Just, to explain, if there wasn't this if check here, then this would be classified as a straight up heap overflow, because it's just a source going to memcpy with a controlled length. So it's a heap overflow. If this if wasn't here, and if this if was unsigned, then this would be classified as a non-vulnerability, because of course this would be a proper if check and it's not exploitable. Okay, so now we saw actually, the automation engine, how it, the score-based analysis, how it actually found one of the vulnerabilities. So let's go to the mitigation part, and here we're going to show both, network-based and vendor recommendations on how to mitigate these sort of vulnerabilities. So the first thing for vendors, and this is, it's funny to say this in 2021, but that we don't have 20-year-old mitigations in place just because it's, the default. It's not just in this day and age, it's usually not performance oriented. Like the embedded processors are fast enough to do these mitigations. So basically for vendors, we're saying, okay, don't use the default compilation flags, actually use common vulnerability mitigations, which can be enabled in the compiler. For example, here, what would definitely solve it, at least for our exploitation method, what we showed, because we exploited the unlink mechanism, is safe unlinking. So this is a very, very well-known mitigation method that when you go to unlink heap node in the doubly linked list, before you unlink it, you actually check that the backwards link and the forward links are proper. So for example, if you're trying to free node B, you're checking that if you go forward and then backward, you end up at B, and the same if you go backwards and then forwards. Of course, in unlinking exploit, the whole idea is that you're changing these links to some crazy addresses because you want to override them. And then if you go forward and backwards or and backwards and forwards, you're not going to end up at the same node because you just linked it to some crazy global address. So safe unlinking, stack canaries here if there were stack overflows, SLR, which this from the devices that we saw did not take advantage of that, and fortify source, which is even stronger than canaries and safe unlinking because it can halt right at the mem copy operation, for example. So we highly recommend these. Also, as always, static analysis and dynamic analysis scanning solutions. As you can see, for example, our static analysis solution found this issue. So it just goes to show that these issues definitely can be found with static and dynamic analysis, fuzzing, etc. And we highly recommend those.
So let's talk about mitigation for network operators, right? And what should they do regarding vulnerabilities such as these in their networks? So we have two types of mitigation there. We have general recommendations and we have specific mitigations related to Infrahalt. On the general side, the first thing you need to know is understand what is on your network, right? And assess the risk of those devices when they connect to the network and continuously as long as they remain connected to your network. And then understanding from this inventory of devices in the network, what is vulnerable and what can or cannot be patched, right? Because we know that in the OT and IoT world, patching is not always easy. In the embedded world, not always patches make it all the way down the supply chain, as we have discussed in the beginning. But also, even if they are, if the patches are available, applying them to a device might be time consuming or difficult because it's a mission critical device and so on. So the second point is segmenting the network to mitigate the risk. So since many of those devices cannot be patched, or even the ones that can be patched should not be, they may be vulnerable to other things in the future, right? And they should not be always exposed externally. The communication in the internal networks should be segmented so that devices cannot talk to basically any other device in the network, but only those devices that they should be talking with. So basically isolating devices so that they cannot be used as entry points for attacks in the network. So isolating them externally, or that they cannot be used as pivot points within the network. So isolating them internally as well to segment, to isolate and mitigate the impact of an exploitation, not just the possibility of an exploitation or the likelihood of an exploitation, but also the impact that it brings in the network. And the third point is actually monitoring the network for malicious packets. So as we have been discussing throughout this presentation, vulnerabilities in TCP/IP stacks, they tend to be very similar, regardless of the TCP/IP stack that is implemented in a device. We have seen several TCP/IP stacks that have vulnerabilities in DNS clients, for instance, several of them that have similar vulnerabilities in the TCP or IP layers, and so on, right? So basically monitoring the network for packets that are malformed, that don't really respect the RFCs, or that are anomalous or that look suspicious, let's say, is a very important point, right? And a sort of a last line of defense as well. If devices are vulnerable, they are not segmented, and an exploitation still happens, then at least somebody is alerted about that, right? In terms of specific recommendations for the vulnerabilities in Infrahalt, we're talking basically about two types of vulnerabilities there, right? The ones on the lower layers on TCP and ICMP, and the ones on the upper layers on DNS and HTTP. For the ones on the upper layers, we tend to recommend that the protocols are disabled directly at the client, or that firewalls and firewall rules can be used to block those protocols if they are not needed, right? So indeed, if the protocols exist in the device, it may be that they're required for the functioning or on your specific network. But if they are not needed, oftentimes they are just misconfigured, right? So that there may be a device issuing DNS requests that are not really necessary in your network. And similarly, accepting HTTP connections, but you don't use the HTTP for anything, or you only use that whenever the device needs to be maintained or configured or so on. So basically making sure that devices only accept the connections that they should be accepting, right? That are needed for their functioning on the upper layers. And on the lower layers, it's not possible to disable TCP or IP and so on, right? But it goes back to what we discussed before about monitoring the traffic, and either you alert somebody when these anomalous packets are found, or you just drop these malformed packets directly at the firewall, which we know that in some environments, such as critical OT environments, it's not always possible to drop packets because that might have a physical impact. But in some environments, it is possible, and when it's not possible to drop the devices, at least alerting for the presence is important. Right. Let's move on to the conclusions and the main takeaways and a little bit of discussion of what we learned during this research. So first, the discussion part, right? So the vulnerability finding and vulnerability research today, it is and it should be manual plus automated, right? It's not one or the other. Automated vulnerability can find low-hanging fruits much easier and much faster than researchers just looking at the code. But manual vulnerability research is still useful for finding more complex issues, right? So for now, there are still issues that are difficult for the automated vulnerability discovery techniques to find, and we believe that in the future as well, that there will be issues that are always more difficult to find, but more and more automated is becoming part of the mainstream, right? And part of the goal of this presentation that we had today is that we help it become part of the mainstream as well by disseminating these ideas. So more vulnerabilities that are found, right, with automated discovery or manual discovery and so on, means that there will be more vulnerabilities to disclose, right? And we want to talk a little bit about vulnerability disclosure here. So in the specific case of Infrahalt, it took more than 9 months to do the whole disclosure process with the vendor, with the downstream vendors, with coordinating agencies and so on. So it's a very long and complicated process where basically the needs and the desires of all these players have to be taken into account up to some point. And currently there's very limited involvement of asset owners, for instance, in this disclosure process. So it's at some points the researchers have to decide who they disclose to, when they do that, and so on. Again, respecting the desires and aligning with all of these players is important, but at some points also we need to move forward in the disclosure process and make sure that more people are aware and so on, right? So what I mean in the second point basically is that as we move to automated discovery, as more vulnerabilities are discovered faster and in types of software that affect the supply chain and that affect several types of devices and sometimes hundreds of vendors at the same time, we as a community, right, the whole research community, the whole vendor community and so on, need to work together on the disclosure process to make sure that things are patched at the right time and that everybody is notified, and so that when things become public, there has been enough time for everybody that needs to be aware of that beforehand. And identifying vulnerable devices without firmware analysis is challenging. Currently, there is no software bill of materials. There is a lot of work on making this a reality, but currently it's not the reality for most of the devices on a network. There is opaque documentation in many cases. There are few network banners and so on. So it's basically not easy to identify devices that are affected by this type of widespread vulnerability, right? Some vendors are still investigating the impact of AMNESIA 33, for instance, which we disclosed in December last year, that also affected TCP/IP stacks. And that's almost a year after the initial disclosure, right? So it's like 8 months now after the public disclosure, but almost a year after we started discussing with impacted vendors. So basically, again, more vulnerabilities are found. If you don't have the right type of firmware analysis tool, if you're a vendor and you don't have the proper SBOM documentation and so on, finding out which devices are impacted is very challenging. Right, but what are the key takeaways then from this research? So TCP/IP stacks have critical vulnerabilities that trickle down the supply chain, right? I think we even in previous work we had already shown that, but this one also specifically for OT, specifically for vulnerabilities that are found automatically, shows that again. And other popular software components could have a similar impact, right? We have been talking a lot about TCP/IP stacks, but you can also think about things such as DNS clients that are not attached to a TCP/IP stack, or web servers, or any sort of software component that, or different types of SDKs in IoT, for instance, that are used by several vendors at the same time, right? And that have this supply chain impact. So basically, there will be in the future for sure many more vulnerabilities of the same type that affect several types of devices and vendors at the same time. Automated vulnerability discovery helps in identifying many of those at a large scale, right? So we believe that this is a turning point for the community. So soon there will be even more vulnerabilities found even faster. It goes back to what we were discussing in the previous slide. Really, the pace of vulnerability discovery is only set to increase, and that has several implications for the community, right? Mitigating these widespread issues involves both the device vendors and the network operators. So it's important that device vendors patch these issues, or hopefully find them even before devices are actually being distributed and sold and so on. But since the world we live in today is that this type of vulnerabilities affect lots of legacy but still active devices, just waiting for patches is not a good solution. So network operators have to do their part as well with segmentation, with looking at malicious packets and monitoring the network and so on. So if you're interested to learn more about this type of research, look at Forescout's Project Memoria website and the JFrog blog that was also put out when we disclosed publicly Infrahalt. And that's what we had to say today. Thank you so much for joining us, and we can keep the conversation open. We'll be happy to take questions and provide some answers and some discussion at the Discord channel. Otherwise, feel free as well to contact us via email or LinkedIn or whatever you want. Thank you so much.